working with Wayne Goodman with some surface science, and then he went to the dark side and started doing real catalysis, and ended up here today giving a keynote talk on SCR catalysis on copper SSD13. What is yours?
Thanks, Janusz, for the introduction. First of all, I would like to thank the meeting organizers very much for this invitation, even though I'm pretty sure that I am not even qualified to give a keynote presentation. Even if I am, I think this is only because of my excellent colleagues from P&L, a postdoc, Martin Kohler, staff scientist, Ying Wang, Janusz Sen, and our group leader, Chuck Pidden. You may realize that I have changed the title a little bit, cutting off the co-cation effects and hydrothermal effects. Those actually will be covered tomorrow in the same room, tomorrow afternoon by Chuck. This page shows the outline. I will give us a brief introduction and spend some time focusing on the nature and location of copper ions, 3 effects from the copper loading, from the presence of moisture, and from SI/EO ratio. And then spend some time to talk about the structure-function relationship in ammonia SCR and related chemistry, mainly NO and ammonia oxidation. This is followed by several conclusions. As we all know that ammonia SCR or zeolite catalyst has been there for more than 30 years. And in the year 2010, there was a major breakthrough in industry that BASF and Johnson Matthey commercialized copper chaperite as commercial diesel engine exhaust after treatment catalyst. From the basic catalytic science point of view, many of us hold the belief that the relatively simple chaperite structure offers a great opportunity for fundamental advancements in the ammonia SCR chemistry. However, from the recent literature, there are still a number of open questions that are answered. Here I selected 4 of them, which we believe are important. First, the nature of catalytic relative copper species, whether they are monomers, dimers, or even bigger clusters, and the most relevant NOx and ammonia species that form intermediates directly. And the third one, which mechanism that best describe ammonia SCR, whether they are Langmuir-Hinshelwood, Ely-Rideal, or even the redox mechanism. And finally, the rules of Brown-Seed acidity. Do they do ammonia storage only, or they are actually involved in elementary steps? In order to answer those questions, our strategy is to make a fairly large number of catalysts with quite dramatic differences in properties, including different SI/EO ratios and different copper loadings, and research on those catalysts. Therefore, we synthesized in our lab 3 different SSD substrates with 3 different SI/EO ratios, 6, 12, and 35. SEM imaging shows that we have a typical primary particle sizes of 2-3 microns, typical for zeolites, and the XRD pattern shows that they are highly crystallized. Then we did a traditional solution ion exchange to load copper into this catalyst. As this table shows that we have a large number of catalysts with copper loading from a very low exchange level to near saturation exchange levels. Next, I will talk about the nature and location of copper ions. First, effects from copper loading. As we all know that zeolites have 2 building blocks, silicon tetrahedron and aluminum tetrahedron. One of them is negatively charged. Therefore, the zeolite framework is negatively charged. It requires extra framework cations to balance the charge. Of course, copper ions do this. And precisely because of this, many of us, including me, are in business. And If we look at this chapter structure, there are actually 4 different types of extra framework cation positions. In the center of this double 6-member ring, close to the windows of a 6-member ring, 8-member ring, or along the symmetry axis. So the very first obvious question we would like to ask is where copper ions are located. The very first model was given by Professor Lobo's group, Pico and Lobo. They published in 2010, and based on studies on a dehydrated sample with fairly high copper loadings, used a traditional method, real-world analysis of XRD. And this graph shows their model. They suggested that all copper ions are located in windows of a 6-member ring with 2 aluminum atoms. There are actually 2 arrangements for this. And our colleagues from Pittsburgh also made some early on studies. They prepared catalyst at a silicon aluminum ratio at 6 and various copper loadings. Then they performed temperature programmed reduction and FTIR TOT evaluation of the zeolite framework. In both cases, they discovered a copper loading dependence. For example, from TPR, at the low copper loadings, there's 1 reduction state. High copper loadings is extra 1. TOT evaluation shows the same story. At low copper loadings, there's 1 copper perturbed TOT vibration. At high copper loadings, another one appears. Therefore, in the year 2012, they published a paper suggesting that there are actually 2 different cationic positions in this material. By the time they made this publication, they were not very confident, so they put a question mark in the title, which is not very typical. But in recent years, it is generally agreed that this is indeed the case. From the most recent studies, both theory and experimental, people do believe that at low copper loadings, copper ions will be located in 6-member ring windows in dehydrated samples. And when the copper loading goes higher, some of the copper also occupy the 8-member rings. Especially interesting is that if the copper ions are located in 8-member ring, they have high tendency to stay as copper OH instead of naked copper 2+. So I've shown that by increasing the copper loading, we are adding some complexities to the copper locations. Still, for dehydrated samples, this is still a relatively simple case. Next, I will show that with the presence of moisture, the situation can be much more complicated. First of all, why we are interested in the presence of moisture? And the answer is very simple. This is highly relevant to applications. This is because the engine exhaust contain 5 to 10% of water vapor. Therefore, SCR catalysts always work in the presence of water. I show this graph here not from us, but from a very strong team by researchers from Notre Dame, Argonne National Lab, and Purdue. They did very careful studies. This graph shows the dense spectra of hydrated, dehydrated, and reduced copper SS13. I only want to point out one thing, which is for a fully hydrated sample at ambient temperatures, the dense spectra look almost like identical to hex-hour copper complex in water solution. This suggests that in hydrated samples, all the copper ions are fully solvated at ambient conditions. So one interesting question to know is what happens when we do dehydration to such a hydrated catalyst. So recently we did this, and we used a number of spectroscopy methods, drift, XRD, DINS, to study the dehydration process of a hydrated copper SSD. We have 2 graphs of the drift shown here, one specifically looking at water desorption, and the other look at the perturbed TOT vibrations. From these 2 graphs, we know that in an inert gas flow, complete dehydration of hydrated catalyst occurs at around 200 Celsius. By the time the water is gone, copper 2 plus and copper OH species move to windows of 6-member ring and 8-member ring. This is evidenced by the perturbed framework vibrations. We can also use another spectroscopy technique, EPR, to directly look at the copper ions. In this case, we studied a low copper loaded sample. If we look at the ambient temperature hydrated sample spectrum, we have in the high field, we have a double lit feature. In the low field, no much copper fine features, which indicates that the copper ions are totally delocalized. This is fully consistent with the Zin's studies. After a dehydration temperature of 250, in the high field, we only see one sharp feature left, and in the low field, there's well-defined copper fine structures. In this case, copper ions are completely localized. And below a temperature around 200, we know that the copper ions are highly mobile. We have two evidences. First, the copper fine features are absent, and second, even in the high field, the overall signal intensity is low. This is caused by quick copper-copper interactions, which demonstrates that the copper ions are indeed highly mobile before total dehydration. So in the presence of moisture, there are a number of copper ion interactions we can expect. The first one being copper 2 plus hydrolysis to form this copper OH species. When we have copper OH species, we can expect there might be some dimerization reactions to form, for example, double-bridged copper dimers or single-bridged copper dimers. This is only in the presence of moisture. You can continue to imagine what happens when we also have other gases present, for example, oxygen, ammonia, and even SCR reactants. So we can imagine that the complexity can quickly build up in these cases. Next, I want to show two examples to show that people are actually recently realized and started to appreciate this complexity. This example shows a theoretical study by researchers from Penn State. They did a molecular dynamic simulation of the diamond formation for partially hydrated copper ions. Indeed, they concluded that the formation of stable dimeric copper species is indeed possible in the presence of water. And another interesting feature is that when this hydrated sample is dehydrated, those diamond species are still stable and they are located in windows of 8-member ring. I excuse that I really cannot pronounce this first author's name. Another example is a study by Giannanino et al. They used UV to look at the dehydration of a number of copper zeolites in the presence of oxygen. Besides the expected isolated copper ions, we seem to also monitor to the presence of dimeric species. There is yet another factor can affect copper ion locations, which is SiO ratios. To study this, we synthesized, as I already described, we synthesized catalysts with different SiO ratios, 6, 12, and 35. We use solid state enema to look at those parent powders, and the aluminum enema shows that our materials are of high quality. The majority of aluminum are in tetrahedral positions. We can also use a silica enema to look at the distribution of aluminum in silica in the tetrahedral positions. And then we synthesized the copper-loaded samples and did a simple hydrogen TPR. Here I give two examples. For our samples with the silicon to aluminum ratio at 12, TPR tells us that there is a high temperature reduction state centered at around 380 Celsius, which is a reduction of copper 2 plus by hydrogen to copper 1 plus. For copper ions that are located in windows of 6 membrane rings with 2 aluminum atoms. And we also have, for the higher copper loaded samples, reduction at lower temperatures. Those can be assigned to partially hydrated copper ions or copper OH species, which I will not give more details. The interesting discovery is that for our SiAl ratio 35 samples, we do not see this high temperature reduction peak centered at 380, which means that we do not have copper ions that are located in windows of 6 membrane rings with 2 aluminum atoms. And the reason is that at such a high SiAl ratio, we do not have such arrangement. And this model is further confirmed by doing NO chemisorption FTIR. For our samples with SiAl ratio at 12, we did a vacuum treatment and then introduced NO to do NO chemisorption. And if the copper 2 plus is located in 6 membrane ring with 2 aluminum atoms, and there is a specific NO vibration frequency occurring at 1948 real numbers. Clearly, we have this strong feature in this sample. And our SiAl ratio 35 sample, this feature is barely there. And instead, the majority of the features are between 1880 and 1920, which are assigned to NO adsorbed copper OH that are located in 8 membrane ring. Our colleagues from Washington State University, Jane Qin and Professor McQueen, they did a theoretical calculation for us, and both and their calculated frequencies of NO matches with our experimental data very well. So we do a lot of spectroscopic studies, and we do a lot of kinetics. End of the day, what we really want to learn is to better understand structure-function relationship in ammonia SCR and related chemistry, mainly NO and ammonia oxidation reactions. So next I will give 2 examples. First on the kinetics, copper loading effects on reaction kinetics, and the second, the effects of bronze acidity to reaction kinetics. At this point, I would like to bring back those open questions that I described at the very beginning of my presentation. From recent literature, you might have been reading this statement quite a lot. First, the copper ions next to windows of 6 membrane ring are the active sites for standard ammonia SCR. And another conclusion that people make is that standard ammonia SCR over chemolite follows a redox mechanism. However, as I just described, there are more than one type of copper ions in this material, especially for the high copper loaded samples. If we assign one type, specific type, as active sites, how about the rest? Are the rest inactive? And the second, if we assume that a redox mechanism describes ammonia SCR over this catalyst, but a redox mechanism is respect to the copper ion active center, how does the reactants interact with these active centers to form, to be activated and complex to form the key intermediates? It's not shown by just seeing that we have a redox mechanism. So in order to understand those things, we did a very careful standard SCR measurements, a number of catalysts. In this case, I show results on a series of samples with SI ratio at 6 and with various copper loadings from low to near saturation. Interestingly, we discovered, even in the differential regime, 2 normal and 1 abnormal kinetic regimes. Normal means as the temperature rises, reaction rate rises. But indeed, there is an abnormal regime between 250 and 350 Celsius, where as we increase the reaction temperature, reaction rate actually decreases. If we think about the reaction-free energy, which is so negative, this behavior is indeed abnormal from a thermodynamic standpoint. To understand this, we did a power law dependence at selected reaction temperatures. So we did reactions at 200, 250, 300, 350. Vary the NO and ammonia partial pressures, and in the end, we didn't find any difference in these reaction temperatures. The reaction is always first order with respect to NO pressure and zero order with respect to ammonia pressure. Therefore, we believe that this abnormal kinetic behavior is less likely caused by changes in reactants, more likely caused by changes in the nature of the active centers. So we further to study more detailed kinetics in the three kinetic regimes. So this page shows what happens in the high temperature regime, 350 and above. At such high reaction temperatures, we have to use samples with extremely low couple loadings, and we have to run reactions at exceedingly high space velocity in order to collect enough data points within the differential regime. Even with this, we are not sure that they are kinetically benign, so that we used this Coral's new work criterion to justify that. Indeed, for our data points collected under differential regime, there is a nice linear relationship between normalized reaction rate and couple loading, which suggests that indeed those kinetic data are nicely without artifacts, meaning without mass and heat transfer limitations. So we then did this Arrhenius plot, and importantly we found that in the linear Arrhenius regime, the thermal frequencies are invariant as a function of couple loading, which is a strong indication that the active centers are isolated couple 2 plus, and at such high temperatures, we only expect that those ions are located in windows of a 6-membered ring. Then we further move on to look at what happens at low temperatures. Low temperatures, we also did this Coral's neural criterion plot, and it's roughly linear from low to intermediate couple loadings. But if we calculate the thermal frequency as a function of couple loading, we realized that only at intermediate couple loadings, the 2F is independent of couple loading. At very low couple loadings, the 2Fs are low, and high couple loadings, 2Fs are low too. And the researchers from Purdue also found a similar thing, that their sample with extremely low loadings also show a reaction rate substantially smaller than their sample with intermediate couple loadings. So this is consistent with the thing that we found here. So using this Arrhenius equation, we calculated the low temperature regime, the prefactors and reaction apparent activation energies. And both parameters actually change as a function of couple loading dramatically. Therefore, in this low temperature regime, the one location of couple ion active center statement that we have made on the high temperature regime cannot be justified. It appears to us that both the accessibility and nature of the couple ions change as a function of couple loading at this low temperature regime. This is what we believe what actually happens is that at such low reaction temperatures, in the presence of moisture and in the presence of ammonia storage, there must be strong solvation effects to the active sites. Therefore, their location and composition can be difficult to determine. So another interesting thing I want to share is that for our samples at extremely low couple loadings, instead of a linear relationship between normalized rate and couple loading, we actually found not a very bad a linear relationship between reaction rate and a square of cup loading. This might indicate that at such low cup loading situations, the actual active centers could be a dimeric species that somehow fall and act as the active centers. And so only in the intermediate cup loadings, we believe that the SCR reaction is probably catalyzed by isolated copper ions. And the active centers, based on our spectroscopic measurements, could be solvated copper 2+ or solvated copper OH species. And because of the solvation effects, their precise location and composition are probably difficult to determine. That's why the kinetics look so complicated. And I use this slide to show, to give explanation to the abnormal kinetic regime between 250 and 350, why the reaction rate decreases as we increase the reaction temperature. From our dehydration studies, we know that this is the temperature regime that the water started to be driven off from the copper sides, and the copper will start to migrate close to the framework. We can suspect that when this happens, the interaction between copper ions and the framework will become stronger as the temperature rises. And somehow, if the copper 2+ species is reduced in this process, and also if the copper 1+ interacts strongly with the framework and hard to be reoxidized, then we might expect a reaction rate decrease. We have some evidence to support our hypothesis. This is from our drift studies by looking at the copper OH species. Indeed, this species, as we increase the temperature, the intensity of this decreases. So this is a simple model that we can give here. So this active center, they might be reduced to copper 1+, and so if this copper 1+ interacts strongly with the framework and hard to be reoxidized back to copper 2+, then there might be an explanation. Okay, the final of my part of my talk is the rules of Bronsted acidity on SCR unrelated chemistry. So we have two questions that we want to ask. First, is Bronsted acidity indispensable for copper chevrolet SCR catalyst? And second, does proton involved in elementary steps in SCR unrelated chemistry? Well, the answer to the first question seems to be very simple. It is absolutely indispensable. There are at least two reasons. First, without Bronsted acidity, there will be no chance for atomic dispersion of copper ions. This is obvious. And also, without Bronsted acidity, there will be no ammonia storage, which is also important for this class of catalysts. The answer to the second question is more difficult. It could be yes, could be no. For example, if we assign the isolated copper ion monomers as active centers, then the redox chemistry indeed requires the participation of protons. This is because if